When we were working our way through the factorization of 7007, I had to know which numbers were prime and which ones weren't to know which things to divide by. So I need a list of primes. And I told you that the list in the textbook is on page 274. Where though did it come from? How do I make a list of primes? Depends on how far you want to go. The easiest way to do it is to cast out numbers that aren't prime. So let's start a list. Let's say I want to go to 100. Well, I'd start right away by telling you 1 is not prime. Two is prime, but then anything that contains a 2 won't be prime. So let's circle 2 and cross out every other number after that. So I've sifted out all of my even numbers. The next uncircled number is prime, because its square root is smaller than 2, and it doesn't have any other factors smaller than that number. So this number must be a prime. Well, if that number is a prime, then any number that has it as a factor isn't. So cross out every third number after that. The next uncircled number is prime. And again, I can say, okay, now what I'm going to do is I'm going to cross out every number that's a multiple of that. So jump by 5s. The next uncircled number, uncrossed out number, that number is prime. Cross out every multiple of 7, even if you've already hit it, right? What's square root of 100? Means every number that is composite on this list had a factor smaller than or equal to 10. We've crossed out all the composite numbers up to 100. I've only got left uncircled or uncrossed primes. And I can go all the way to 100. I've sifted out one layer at a time. Top of page 274. They don't cross out, they underline. Okay, 2. Everything other than 2 that's even, underline it. Everything other than 3 that's multiple of 3, underline it again. Everything under 5, everything under 7. Those are all the primes less than 10. Every underlined number in that last table is prime. I've sifted out every composite. 41 is prime, 43 is prime, 59 is prime.
They didn't underline 1.
Ah, but they didn't not underline it either, did they? Technically, 1 shouldn't be on the list. It should be crossed out because it's not a multiple of 2. It's not a multiple of 3. They only underline multiples. I should throw out 1 by default because we say 1 is not prime to keep our factorization. So as a matter of fact, if you look in the textbook, it's a little hard to see up here. The numbers 2, 3, 5, and 7, as they go along, change color. 1 is black, 2 and 3 are blue in this picture. It's very difficult to see here. It's a lot easier on the page. So I can say, oh, look, all of the blue numbers, you can tell? Me neither. So that's an easy way. It's a very deliberate, it's not a very fast way the big O of this operation? Unfortunately, no. I'm very happy that it's not big O of n factorial. We need it forever. N factorial is really big, hundreds. Squared. It's actually smaller than n squared. I have to go through my list. The list goes all the way up to n. But I only have to go through the list at most square root of n times. Because I have to go through it for each prime less than the square root of n. So it's big O of n to the 1.5, or n square root n. It's smaller than big O of n squared. Way smaller than big O of n factorial. You can do this for as big as you want. You want the first 1,000 primes, you can chuck this into a calculator, be done in a second. This is a very easy to code algorithm. Questions? That's why right here, we have all of the non-underlined numbers from that last table. That's a good thing to have on hand. That was the hint problem. How many primes are there? How do I know that there isn't many primes? A great claim.
And you're never gonna just rule out all in and
I would like to know how to prove that. That's a great idea. I would like to say that the following is true.
Because it has the same continuity as natural numbers, and it is 1-to-1 because you got rid of one.
In order to do that, I need to create a function that's a bijection from the natural numbers to the primes. So you need to tell me a formula that will, if I give it an n, spit out the nth prime. So the first prime is 2, the second one is 3, the third one is 5, the fourth one is 7. What's the 233rd prime? I don't know. I could try and build such a bijection, but I can't do it without the function. So I don't have a prime generating function. I'm not sure that's the way to go. But if I could build that one-to-one correspondence and get the same cardinality, I'd be thrilled.
The previous example or the page of the textbook,
Uh-huh.
we were able to like keep grabbing a list. Like if 2 was a prime, kept our multiple to 2. Okay, then
Right.
3. Couldn't we just do that with n? Just keep going up and up and up until you have n items in that list.
Okay, but that only shows me a finite number of primes. If I want to get all the primes less than 100 million, that's less than 100 million things. That's not infinite many things. I then have to somehow take a limit of that thing. Dude, I have enough trouble with limits in calculus. I want to try and do limit infinity here. No, that's not going to work. But I like the idea that it's finite, right? If you say, hey, all the primes up to here, that's finite. My claim would be, if that were true, what happens when we look at other numbers? So let's do this as a proof by contradiction. Remember that, people? Gosh, I tried to purge that out of my brain. Sorry, no, we still need it. How do I prove something by contradiction? That would just prove it to be false. If I found a counter example, I know it was false. But if I'm trying to prove by contradiction, I start with an assumption. Assume what I want to prove is false. So let's assume that there are only finite number of primes. I'm going to put them in order smallest to largest. So P1 is 2, P2 is 3, P3 is 5, on up. And I stop at some point. There are no more prime numbers after this. I don't know what that is, but it's a big number. Now I need to show that this is wrong. So I need another number.
Pn plus 1.
There is no such thing as Pn plus 1. These are all primes. There is no, I listed them all, damn it. There are no more primes. If the only primes I had were 2 and 3 and 5, I could think of the number 30. 30 is divisible by 2 and 3 and 5, right? What if I took 31? Then it's not divisible by 2, it's not divisible by 3, it's not divisible by 5. I have more primes. Here's a new number. I'm going to take all of the numbers in my list, multiply them together. Then I'm going to add 1. I have a problem. That number is clearly bigger than Pn. If it's bigger than Pn, what kind of a number must it be? Unfortunately, no. It can't be prime. All of the primes are smaller than or equal to Pn, and this number is bigger than that. So it can't be prime. But what does that mean? If it's composite, it must have a prime divisor. I don't know what that prime divisor is. I don't. I have no idea. But what happens when you divide Q by any one of the P's in my set? You take this number, you divide it by one of the numbers up here. Seth, you just leaned your head back and went, oh,
It has to be 1.
there's a remainder of 1. Do any of my primes divide Q? No, they all have a remainder of 1. We must have a prime divisor, but it's not in my list. What does that mean about my list? Say it again.
It's not complete.
It's not complete. I missed a prime number. Did I tell you how big the set of primes was? No, it's 100 gazillion things. It's just finite. It doesn't matter how big the list you made is. If you stopped, you're not done. There's some other prime number that's not on your list. If there's some number I missed, no matter how big I made the list can't be finite. The set of primes must be infinite. I still don't have a formula for making these. But I don't need one. I don't have to find that one-to-one and onto function, Emily. I could if I really tried to work at it, but it's not going to work very well because that function goes on forever and I don't know how to form it. Questions? Someone somewhere said there should be a function that lists all the primes. I don't know what it's called. In number theory, they call it pi of n. The function whose domain is the natural numbers and whose output is in the integers. Problem. When I go to figure out what this function is, nobody can figure it out. We can figure out where the primes get distributed. As you get further up the list of numbers, primes get fewer and fewer. The gaps between primes get bigger and bigger and bigger and bigger as you go off to infinity. So we can roughly say that this function happens to be big O of log n. But right now, that's about all we know about that function. The bigger the numbers, the larger the gaps between primes. There are a large number of open problems about primes. Things we just don't know yet. Things like this is a conjecture. It's called the Goldbach conjecture. Nobody knows if it's true or not. Here's another version of the Goldbach conjecture that they did a little more work and they said, all right, well, what if we look not just at any number bigger than 2, but what if we only looked at odd numbers? I may not be able to get all the way down to 2, but I can try looking at 3. By the way, this is known to be true. for numbers up to 10 to the 43,000th power. Numbers of 43,000 digits. That's true. Every odd number can be written as 3 primes added together. Let me go back to our table on page 274 for a minute, and let me notice a couple of interesting things about the list of primes here. Take a look here, 11 and 13, 17 and 19, 29 and 31, 41 and 43, 71 and 73. These are primes that differ by 2. Here's a question for you. Is the set of primes that differ by 2 finite or infinite? We call those things twin primes. Two primes are twin if their difference is 2. Nobody knows. That's a question we don't know the answer to yet. I showed you the great internet Mersenne prime search. The Mersenne primes are primes of the form 2 to a p minus 1. Mersenne thought this worked really well. And he did his calculations by hand in the 1600s. And Pierre Fermat said, well, wait a minute, what if we looked, instead of just any prime, we looked at powers of 2. And instead of subtracting 1, we added 1. So these are called Fermat primes. And again, by hand. Fermat showed that for n is 1 and 2 and 3, this works. It turns out that both of these fail. The bottom one fails when n is 5, 2 to the 32nd plus 1 is not prime. The top one fails when you use 31, 2 to the 31st minus 1 is not prime. Oh, crap. What if I looked at moduli? What if I looked at primes that were of the form 4 something plus 1? David Hilbert in the 1900s looked at the set of primes of this form. Now, really, if you think about numbers that are prime, when you divide by 4, you're either going to get 1 or 3, with one exception, the number 2. Other than that, all the other primes are odd numbers, so the remainder is either 1 or 3. And Hilbert found that there were more primes that looked like this than there were primes that looked like 4k plus 3. Can you prove that that's true all the time? It's been tried. That's his conjecture. There are a lot of pieces of discussions of how prime numbers work that still go forward. I would love to do nothing but number theory for another couple of weeks and show you the dozens of other interesting facts about primes and the way they relate to each other. There's a whole lot of it. Instead, I'm good cheating. Because it isn't always just primes that matter. Before I move on. Question. It turns out the distribution of primes is also related to another one of our $1 million Clay Math Institute prizes. It's related to the Riemann zeta function, which is a function about complex numbers and where this function is equal to 0. And that turns out to be related to a product involving primes. So again, there's another way to get $1 million. I instead want to look at relative divisibility. Instead of just looking at whether or not something can only be divided by 1 and the number itself, the definition being prime, I want to look at pairs of numbers. What things divide these two numbers at the same time? I'm pretty sure y'all have done this before. Back in arithmetic in grade school, where you found greatest common factors, least common denominator, things like that. It's all related to the same idea. What's the greatest common divisor? 24 and 84. I'm sorry? Unfortunately, no, there's a bigger one. But how did you get 3?
I know that if you add the two numbers together and they are common factors, if they're 5 and 3, it was 3.
Aha.
So it's divisible by 3.
Things that are divisible by 3 have numbers that when you add them up are divisible by 3. 24, 2 and 4 make 6, that's divisible by 3. 84 is 12, 12 is divisible by 3. That's true, but that's not the only divisibility issue I can have. Because clearly these are also both even, right? So divisible by 2 as well. So divisible by 2 and by 3, it must be divisible by 6. So I have a greater divisor. I can keep looking. Well, how do you know that's the biggest?
Because if you divide 84 by 12, you get 7, and 7's a prime, so it cannot be broken down any further.
So I could start looking at all the possible divisors of 24. 24 is 1 times 24. It's 2 times 12. It's 3 times 8. It's 4 times 6. Notice how those pairs of numbers get closer and closer together. 24 is not a perfect square, so I don't end up with something squared in the middle. I do 84. 84 is 1 and 84, 2 and 42, 3 and, it's got to be divisible by 3 and something, right? 3 and, you have calculators. You do not have to do this crap in your head. 3 and what? 3 times what gives me 84?
28.
4 times 21. It's not 5. 6. We said it was divisible by 6. 6 times 14. 7 times 12. Anything else? Well, the only other option would be 8, right? Because at that point we'd reach the square root. And if the square root, there's got to be a factor smaller than the square root. So there we go. And then I say, oh, look. The largest number that appears on both lists is 12. There are a bunch of other numbers that appear on both lists. But the biggest one is 12. All right. This requires me to look at all possible divisors of the number. Ew. This is a trick question. This is a trick question. What numbers divide 51? 1 and 51, and not 2, 3. 5 and 1 is 6. 6 and 2 is what? 3 times 17. That means the biggest number that divides 51 is 51. What numbers divide 0? All of them. 0 divided by 51 is 0 with 0 left over. 0 divided by 173 is 0 with 0 left over. The greatest common divisor of 0 and anything is the anything. As long as A is not 0. Remember when I said your greatest common divisor, they can't both be 0. The only things that divide 3 are 1 and 3. 3 doesn't divide 100, but 1 does. Two numbers whose greatest common divisor is 1 are called relatively prime. Hey, wait a minute. If I'm using relatively prime here, then primes must have something to do with greatest common divisor. I haven't done about primes yet. Where are my primes up here? I haven't done anything about primes. What is the prime decomposition of 100? We said you could take any number and write it as a product of primes. It was the last thing we did on Monday. What are the primes that I need to make up 100? Keep going, because it's not just 2 and 5.
It'd be 2 times 3 times 5 times 5.
Right. I need the whole prime decomposition, not just what primes are there, but how often do they show up? And with 3 is just 3. Now I get the idea. My numbers are relatively prime because they don't share any prime factors. the primes in one don't appear in the other, and vice versa. So what if my greatest common divisor isn't 1? We had one where the greatest common divisor was 12, right? Let's go back and look at 24 and 84 again. I know that's 12. But instead of figuring out by listing all the divisors, let's write the prime decompositions again. Brent, you started to give me this one when you said 84. 84 was 12 times 7, and 7 was prime. But 12, what's the prime decomposition for 12? Dominic?
Squared and 3.
So 84 is 2 squared times 3 times 7. What's the prime decomposition for 24?
That's 3.
8 times 3. They have primes in common now. Technically, I could say that 24 has no 7s in it, right? So I could say it's got 7 to the 0 up there. No 7s. Take each prime and pick the lower power. Smaller power up here would be a choice between 2 and 3. Smaller power up here would be a choice between 1 and 1, because it's 3 to the first. Smaller power here would be the minimum of 0 and 1. So that's 2 squared times 3 to the first times 7 to the 0, and that's 12. If I can do the prime decomposition, I can get the greatest common factor just by looking at the primes. This is much faster, but it requires me to know the prime decomposition. And as we saw on Monday, factoring into primes takes a while, and it takes a list of primes. So I could be here for quite some time trying to do this. But if my numbers are small enough, or it's easy enough to find their prime decompositions, this is fairly quick. Prime decomposition of 120. A bunch of you just started staring off into space. You own calculators. You don't have to do this in your head. I don't want you to do this in your head. We're going to get to much bigger numbers in a minute. Doing it in your head's a pain in the ass.
2 cubed times 3 to the first times
500 is 5 times 100, but we already know 100. 100 was 2 squared, 5 squared. I get another 5, so that's 2 squared, 5 cubed. My greatest common divisor then is 2 smaller power squared, 3 smaller power 0, and 5 smaller power 1. My greatest common divisor is 20. Poof! Grab your calculators for me. What's 500 times 120? Say again? 60,000. the positive number L, so that A divides L and B divides L. Notice we're going the other way. Instead of being divisible into A and B are divisible into L. It's called the least common multiple. This is your denominator thing for lowest common denominator. What's the least common multiple of 120 and 500? Now I could do this the hard way. I could start listing out all the multiples of 120 and all the multiples of 500 and see where I run into the same thing. I'll be here for a week. So let's take our prime idea again. Let's go back and look at those prime decompositions up there. This time I want something that divides in. I want 120 to go into it. That means I don't need the smaller powers here. I need the bigger powers here. If I took a number that was bigger than the third power of 2, then it would fit. If I had at least 1 3, it would fit. If I had at least 1 5, it would fit. If I had powers that were bigger than this or equal to it, I would know I could divide in. But the same thing needs to be true here. In order to make this divisible by 500, it has to have at least 2 2s. It has to have at least 5 3s. So here, where I took the smaller power, I now want to take the bigger power. Instead of minimum, I want to use maximum. Now, in this case, again, those are still 2 and 3. These are still 1 and 0. And this is 1 or 3. So the bigger powers, that's 2 to the third, 3 to the 1, 5 to the 3. What's that? $3,000 divided by 500. $3,000 divided by 120. Say again. 25. Notice which primes did get extra. I needed 2 more 5s here, right? 2 cubed, 3 to the 1, 5 to the 1. I needed 2 more 5s. That's why when I divide by 120, I got 25. I needed 1 more 3. 3,000 divided by 500 was 6. Need 1 more 2 and 1 more 3. There's my 6. What was 120 times 500? Say again. 120 times 500. 60,000. What's 20 times 3,000? Why? We picked the bigger power, right? We also picked the smaller power. Multiplying the bigger by the smaller is the same as just multiplying the 2 numbers together. Didn't we prove that when we did proof by cases? Without loss of generality? Remember that proof? That's why we hated that proof. Problem with this idea is that finding this decomposition is not trivial. Breaking something down into primes is a pain in the neck. I would like to find the greatest common divisor of 2,547 and 333. Finding the prime breakdown for 333? Well, that's a small enough number. What's 333 divisible by? So it'll be 3 times 111. What's 111 divisible by? Because its numbers add up to 3. So that's 3 times 37. Prime decomposition of that. Is it divisible by 3? I know it's not divisible by 2. Why is it not divisible by 2? It's an odd number. Is it divisible by 3? Yes. 3 times? Wait a minute. 8 and 4 is 12 and 9 is 21. That's divisible by 3 again. 3 times 3 times. Dividing by the 200, 83. That's not divisible by 3 anymore. Crap, I'm going to have to figure out whether or not that's prime. It's not on my list because it's bigger than 100. 283 is prime. Sure it is. How the hell am I supposed to know that? Maybe it is, maybe it isn't. I don't know. Am I lying to you? You'll have to do some work to figure it out. So let's run with this for a minute. There needs to be another way for me to figure out the greatest common divisor here rather than breaking this into primes.
Square root, and then only use the primes that are from the square root of it.
Well, that would tell me whether or not 283 is prime. But that's great as long as my number is small. Like 283 is square root of 283 is like 17 something. No, I'm going to be here for quite a while. Right? And if I gave you a 5 or 6 digit number, shoot me now. That sucks. I don't want to do that. There's got to be a better way to do this. Fortunately for me, there are several better ways to do this. I need to remember an interesting fact proved way back by Euclid. That when I divide two things, if I divide by some number, then their difference is also divisible by the number. This is short enough I can write the proof in one line. If D divides A, then A is N times D. If D divides B, then D is M times D. Then I get N minus N times D. It's divisible by D. How the hell am I going to make this work for me? That's the thing we will do first on Friday. Because I just ran up against the clock. They finally put one in this room. So I will see you all on Friday. Have a wonderful rest of your day. If you came in late and I still have your homework, come get it from me. Otherwise, I will see you on Friday.